Hello everybody, welcome back to another online lecture for general chemistry. And in today's lecture we're going to be talking about limiting reagents, sometimes also called limiting reactants. Those two terms are interchangeable. Theoretical yields and percent yields. Now I just want to mention this is a very important lesson, especially for those of you that are going to be headed into organic chemistry, because whenever you run organic chemistry reactions, it is a very common thing to turn around and calculate which reactant is going to be the limiting reactant, and then subsequently how much of your product you should be producing, which is in reference to theoretical yield, and then your percent yield is sort of like your success for your reaction based on a certain percentage. So let's define what each of these actually are. So when we talk about a limiting reactant, the limiting reactant is the reactant that will run out first during a reaction, thus limiting the amount of product produced. So if you imagine, whenever I have a reaction, right, I've got the reactants and they're supposed to mix together in order to give me the products. So if I have reactants and they're combining together in some sort of, maybe it's an exchange, maybe they're adding together, there's different types of reactions. But if I'm using each of those pieces and I have a limited amount of one in comparison to the other, one of those two reactants is going to run out before the other one. And we would refer to that as the limiting reactant. Theoretical yield, by definition, is going to be the maximum amount of product we could produce in grams if our reaction is 100% successful. And then finally, percent yield is, again, I mentioned sort of a success rate. The percent yield is really just your actual yield, or the yield you actually get in the laboratory experimentally, over your theoretical yield. So you divide the two of those and you get a decimal. If you times it by 100, that's going to give you percent yield. And that's, again, sort of a way of measuring how successful the reaction was. You should not be going over 100%. If you do have 100%, that means your actual yield is equal to your theoretical yield, that you maximize the most product that you could possibly produce. All right, so let's discuss how we would calculate each of these. There's a couple of steps. So starting out, and these will all encompass one another, you're going to see that in order to calculate theoretical yield, you have to calculate limiting reactant. In order to calculate percent yield, you have to calculate theoretical yield, which subsequently requires you to calculate limiting reactant. So we're going to start with limiting reactant and work our way up. So in order to calculate a limiting reactant, you're going to need a couple of things. First of all, you have to have your equation balanced. Now, in this video, I'm going to be using balanced equations. However, if you are not comfortable balancing a chemical equation, you should go back and you should watch the video or the lecture on balancing equations. That is something that you need as a skill set leading up to this. Now, once you have your balanced equation, the first thing you want to do is convert any reactant that you have in terms of grams into moles. And again, this is something that should be familiar as well. When we're converting from grams into moles, we're using the molecular weight from the periodic table. If you have issues with that, you can revisit the video on turning grams to moles and moles to grams, going back and forth and converting like that. So the first step, we balance the equation, and any grams of reactant should be converted into moles. That's the first step. The second step is that we're going to convert moles of reactants into moles of product using a mole-to-mole ratio. Now, this is where students can sometimes get lost, because you're used to doing grams to moles and moles to grams, etc., back and forth up to this point. However, this sort of introduces a new idea that we can go from moles of one compound to moles of another compound. And what we're going to use in order to figure out that ratio are the stoichiometric coefficients that come in front of the reactions. So if I gave you a simple reaction like this, 2A plus B goes to 3C. So A and B are added together and they give you C. 2A plus B goes to 3C. The ratio, the mole-to-mole ratio of A to C is 2 to 3. And so that's the mole ratio I would use when setting up the equation. If I wanted to find the mole-to-mole ratio of B to C, I would say it's 1, there's an implied 1 with this B here, to 3C. So it's 1 to 3. So this is basically an extension. If you were setting up a canceling table or you were multiplying through, however you decide to work on your conversions, if you were to convert grams into moles, the next step would be a mole to mole ratio, where on the bottom you're going to cancel out the moles of reactant, and on the top you're going to put the moles of product, and those numbers are going to be found as the stoichiometric coefficients, or the large numbers in front of each of these reactants and products. And as we practice, you'll get used to this. All right, so number 3, the lowest product production is going to be the limiting reactant. So if I take a look at both of these, I'm going to set these up, I'm going to figure out how many moles of product each of these reactants could theoretically produce. Whichever one is going to run out first is going to produce less product, and therefore it is inherently going to be my limiting reactant or limiting reagent. And so that's all there is to finding a limiting reactant or a limiting reagent. You need to go through, turn any grams you have for each reactant into moles, convert the moles of each reactant into moles of product, and then compare those moles of product and say which one's going to be the lesser amount. Whichever one is going to be the limiting reactant. Now it's also, I want to point out here, this is important because we're dealing with moles. So if I just say, for instance, you have 1 gram of hydrogen and 1 gram of nitrogen, well, you're going to need to look by converting those into moles, and you also need to look at their mole to mole ratio to the products in order to predict this. So I can't say, oh, well, those would both run out at the same time because they're each 1 gram. 1 gram of hydrogen is going to have a different number of hydrogen atoms than 1 mole of nitrogen would. Okay, I'm sorry, 1 gram of nitrogen. A mole of each would have the same amount. But the grams, because they have different molecular weights, are going to have different amounts of those individual products and those individual molecules. Okay, so that is limiting reactant, and we will practice this when we tie it all together. The next thing we want to talk about is theoretical yield. And for theoretical yield, you're going to extend this one step further. You're going to use the lower number of product moles, so whichever moles came out for your limiting reactant, and convert that into grams of your product. So this is a molecular weight conversion from moles of product into grams of product. Once you've done that, that's your theoretical yield. Again, a theoretical yield is the maximum amount of product you could obtain based on your limiting reactant. If your reaction was 100% successful, there were no interfering side reactions or anything else like that. So that is theoretical yield. Whatever number you get in grams is the most that you could get for that given reaction with the amount of reagents or reactants that you initially started with. And so then we move and we have percent yield. And again, percent yield is probably the easiest one to understand, but it also relies on information from the other two, as you can see these leading to one another. Percent yield, all you need to do is divide the actual yield with the theoretical yield. So you have actual yield up here in the numerator, and theoretical yield, which is your maximum amount, in the denominator. Think of it just like a test, right? If there's 100 points on the test, your actual score goes on the top. You get a percentage. It tells you how well you did. Same thing. We're dealing with grams here, but the maximum number of grams go on the bottom, the theoretical yield you calculated. The actual number of grams that you were able to obtain in your experiment or in the lab go on top. And then we take that, that'll give you a decimal, and that decimal represents the percent yield. So hopefully these 3 subjects make sense and you understand them. Here's an equation. I have nitrogen monoxide, and I'm going to react that with hydrogen gas in order to form ammonia and H2O. Now again, as I said before, I'm going to have these balanced, so they're already balanced here in this reaction that you see. And here's the question. To start, I want you to find the limiting reagent if you wish to produce ammonia, so NH3 is what's of interest here, with 86.3 grams of nitrogen monoxide and 25.6 grams of hydrogen gas. So go ahead and pause the video and attempt to solve which one the limiting reagent would be, and I'll put up the answers here in a minute. Okay, so welcome back, and hopefully you were able to follow along with this process. So to start with, I want to compare the nitrogen monoxide and the hydrogen gas. I was told that I had 86.3 grams of the nitrogen monoxide. If I go to the periodic table and I add up nitrogen and oxygen, I get 30.01 grams for my nitrogen monoxide, and that's for every 1 mole. So that's how I start this. And then I look up in the equation. Now on the bottom here, I'm going to have moles of nitrogen monoxide. And at the top, I'm going to have the moles of ammonia. Well, some people may have put that this is 1-to-1, but just for the sake of understanding where this came from, I'm going to put here 2 moles of nitrogen monoxide to every 2 moles of ammonia. And if we go up and we look at the equation, where are these numbers coming from? Well, here's the 2 for the nitrogen monoxide, and here is the 2 for the ammonia. And so if you calculate all that and you solve it, you get 2.88 moles of ammonia. So we follow the same process, which I'm going to put up here. 25.6 grams of hydrogen, 2.02 grams of hydrogen for every 1 mole of hydrogen. Now remember, this is H2, so it's 2.02 instead of 1.01. It's not just a hydrogen atom. Hydrogen is a diatomic gas, so it's 2.02. And then if I look at the ratio, here's hydrogen on the bottom to cancel out the other mole of hydrogen up top there. And I want to get into moles of ammonia. I have NH3 up top and H2 at the bottom. It's 2-to-5 based on the numbers I find in the balanced equation. I solve all of this and I get 5.07 moles of ammonia. So if I compare these, the nitrogen monoxide can produce 2.88 moles of ammonia. The hydrogen can produce 5.07 moles of ammonia. And so it's a very clear-cut case here that the nitrogen monoxide is certainly my limiting reagent. Now, the next thing I want to ask is, can you find the theoretical yield of ammonia and the percent yield if you obtained 45.5 grams of NH3? So that 45.5 grams that I'm telling you here, that is your actual yield. That's what the actual yield is. So I'm telling you that's how much you obtained in the lab. So find the theoretical yield for ammonia and the percent yield, given the work you just did, if you really obtained 45.5 grams of ammonia when you ran this reaction. So we take the limiting reactant, which is the nitrogen monoxide. We found that it could produce 2.88 moles of ammonia, and so we have that there. We're then going to multiply through by the molecular weight of ammonia, which if you go to the periodic table and add up nitrogen and 3 hydrogens, you should get 17.04. And then if we solve that, you should come out to 49.0 grams of ammonia. And so the theoretical yield of ammonia is 49.0 grams. That's the most we could obtain. So now, if I want to figure out the percent yield, I need to take the actual yield, which in the question we said was 45.5 grams, and I'm going to put that over 49 grams, because that's my theoretical yield, and I'm going to go ahead and just add this in as the percent. You would multiply by 100 once you get that answer, but what you should end up with is 92.9 as your percent yield. All right, so here is another problem. I'm going to flash up on the screen. Here's your equation, and here's the problem. So I want you guys to work on this problem, pause the video, and I will put up the answers afterwards. So go ahead and pause the video now, and I will put the answers up afterwards. If you have issues with it, go back and watch what we just did previously. So go ahead and pause. All right, guys, welcome back. I have the setup here. I'm not going to run through this in quite as much detail as I did the first time, but you can follow the setup. I have the grams of each of these, and I'm converting these using a multiple ratio into the moles of iron, because that's what the question was asking for. It wanted to find the limiting reactant, and it's interested in the iron. So the iron oxide gives me 2.09 moles of iron, and the carbon monoxide gives me 2.04 moles of iron. This is a lot closer than last time. But when we go through this calculation, we can see that the carbon monoxide is the limiting reagent. So if we use that and we continue on with iron, we can find that the theoretical yield using this equation down here is 114 grams. And then the question told us that we had 72.3 grams for our actual yield. So if we divide that with 114 grams, we see that the percent yield is 63.4%. So hopefully you guys found this helpful. If you have questions, feel free to leave them in the comments or to contact me. As always, I appreciate you watching and taking the time to learn. Please remember to like the video, comment, and subscribe for all the latest updates, and I will see you guys here for the next video. Thanks a lot.